Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of this course on robust control. So, in the previous lecture we have seen a few detailed descriptions drawn heavily from matrix theory. Particularly we were interested in these symmetric matrices or Hermitian matrices if you are dealing with complex matrices, that is, right. And we have seen that if the matrix happens to be Hermitian, square Hermitian matrix of size n cross n, then its eigenvalues must all be real, right. We have proved that. And then subsequently we moved into this description of what is an inner product. Now, of course, an inner product is a much more generic, all encompassing term, but we are here specifying a particular type of inner product which is very familiar to us, that is something that looks akin to the dot product, right. The only thing you have to remember in this is that you have to take the complex conjugate of the individual entries while taking the dot product, okay. So, that is how this inner product is defined. And then we saw that if you have a bunch of orthogonal vectors, why can we define orthogonal vectors? The moment you have an inner product defined, then it makes sense to talk about whether a pair of vectors are orthogonal to one another, right. That is, if their inner product happens to be 0, then we say that those two vectors are orthogonal to each other, right. And once we have this idea of what this orthogonality entails, then we can say safely that if you have a bunch of orthogonal vectors such that you take any two vectors and take the inner product between them and it will lead to 0, then we can say that the following is true, that if we have that each of those individual vectors is of unit norm. Once again, what is a norm? The moment you have an inner product defined, a norm is automatically induced, in the sense that if you take the inner product of a vector with itself, you get the norm squared of that particular vector, right. So, then we see that if you have a bunch of orthogonal vectors, each of which has a unit norm, right, then you call them an orthonormal set of vectors, okay. And one of the interesting properties that we shall start today's lecture with, the first thing we shall cover is that when you have a bunch of orthonormal vectors, right, then they are bound to be linearly independent. The same is not true of an orthogonal set of vectors, and we shall just highlight that point shortly as to why it is so. So, let us consider C1 V1 plus C2 V2 plus dot 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 till Ck Vk, right. So, remember in the previous lecture we have already defined this set S to be a bunch of vectors, each of which is orthogonal to every other vector in that set, right. Okay. So, that is how it is defined here. Whenever I is not equal to j, the inner product of Vi with Vj happens to be 0, right. So, now in addition to that we are imposing this orthonormality condition, that is, each of those vectors has a unit norm. Then what happens? Now, suppose this is equal to 0. If it is indeed linearly independent, then it must so turn out that each of these Ci's, that is C1, C2, C3 through till Ck, must also be 0 under this given condition. Let us see. So, let this be V, okay. So, suppose a V is given as a linear combination of these vectors, or that it belongs to the span of this set of vectors S, okay. That is just another way of saying it. Now, if we take, for example, the inner product of V1 with respect to V, right. What do we get? We get that this is C1 times V1 inner product V1 plus C2 times V1 inner product V2 plus so on and so forth till we have Ck times V1 inner product with Vk, and this will also be 0, because of course if you are taking the inner product of a vector with the 0 vector, it should eventually lead to the 0 vector. That is how the description is, right. That is straight away it follows from the definition of the inner product, yeah, because this is how we have described the inner product, and if the inner product happens to be equal to 0, then we say that, well, the vectors are orthogonal, right. So, now if this is true, then what happens? Look, this just implies that each of these terms are anyway 0. So, apparently the only non-zero term here is this. Why are each of these 0? That is because V1 inner product with any other Vk when k is not, or Vj when j is not equal to 1 is going to be 0 by the tenets of orthogonality, right. And now, therefore, we can conclude from this preceding step that this implies C1 is equal to 0. Why? Because after all V1 Hermitian with V1 is equal to 1 squared, because V1 is of unit norm, because of the orthonormality now. On the other hand, you see, if this orthogonal set contains the 0 vector, yeah, any set of vectors containing the 0 vector can never be linearly independent, because you take this linear combination of that set of vectors and assign a non-zero weight or non-zero scalar to the 0 vector, and you have a linear combination, a non-trivial linear combination which will lead to 0. So, therefore, when we say that the set of orthogonal vectors is not linearly independent necessarily, it means you are admitting the possibility that the set potentially contains a 0 vector. But the moment you say it has got to be an orthonormal set, well, the 0 vector, there is no way you can make it a unit norm vector, its norm is always going to be 0 by default, right. So, therefore, when we say it is an orthonormal set of vectors, only then you can venture and say that, well, then it must be linearly independent. One of the next another important property and consequence of this is, we have seen that a set of vectors linearly independent vectors can be extended to become a basis for the underlying vector space, right. So, suppose now here we have the underlying vector space is Cn, n tuple of complex numbers, okay. So, this is our vector space V, and we have this set which is an orthonormal set of vectors, orthonormal, hence linearly independent as we have just shown you. So, let us say this is V1, V2 dot 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 till Vk, okay, and clearly k has to be less than or equal to n. If k is greater than n, then, well, you know, it violates the condition. On the one hand it is linearly independent, and on the other hand it contains more than n vectors, yeah, then it cannot have cannot be a set of linearly independent vectors in an n dimensional vector space, because the dimension is basically that number which is giving you the largest size or largest cardinality of any linearly independent set in that vector space, right. So, you cannot have more than n linearly independent vectors, yeah, in a set of vectors which originate from or which belong to a vector space of dimension n, right. So, therefore, this k must be less than or equal to n. Okay. Having seen this, of course, it is trivial to say that this set S can be extended to a basis for V, which is C to the n here, right. More importantly, the claim here is that S can not only be extended to a basis for C, but S can be extended to a not just any basis, but rather to an orthonormal basis for Cn. This is interesting. Why? Because obviously any linearly independent set can be extended to a basis, but now I am saying that if the set happens to be orthonormal, then you can do more. not only can you extend it to a basis for the vector space, but you can also ensure that that basis that you will have will also be orthonormal itself, right. So, why should this be true, or why must this be true? Remember, this result is true for any vector space, any inner product space like this, but we will only talk about the specific case that is of our interest here. So, our proofs will be accordingly simpler. Okay. So, we are only particularly concerned with this C to the n, this vector space. Okay. If you want the general proof, you can go through any standard textbook on linear algebra and you will have it there. So, I will just give you a flavor of how we and why we can claim this to be true. Okay. So, let us see. Now, suppose you cook up this matrix V like so. So, this is V1 star, V2 star dot 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 till Vk star. So, what do these look like? V1 star is basically a row vector, yeah. So, this is basically an n tuple, right. So, this is a k cross n vector, where of course, each entry of V1 is the complex conjugate of the corresponding entry of V, and instead of the column you have it written as a row. So, what can you say about this matrix? Well, for one, k is less than equal to n, and therefore, it implies that if k is strictly less than n, then V has a non-trivial kernel. Why am I saying this? Just let us go over this a little slowly, so that these ideas are crystallized. What does this mean? This is what we call a fat matrix, which has more columns than rows. Yeah, it looks fat, right, or a wide matrix, different parlance. Now, that essentially means that what can the rank of this matrix be? We know that again I have not proved that, but we know that the row rank and column rank of a matrix are identical, which means that the number of linearly independent rows and the number of linearly independent columns in a matrix are one and the same, right. So, if you do not have any more than k rows in a particular matrix, then the rank of the matrix cannot be more than k, right. In other words, your rank of this matrix can at most be k, right. But what do we know about the rank nullity theorem? From the rank nullity theorem, what can we deduce about this, right. So, remember, the rank nullity theorem says that, recall. So, this is something we have taken some pains to prove, and even in the abstract sense, yeah. So, what do we know about the rank nullity theorem here? So, we know that the dimension of V, which in our case remember is basically C to the n, and therefore, this in our case is equal to n, right. That is the dimension of V, the domain. That is going to be equal to the dimension of the image of this linear map, which in this case is V, plus the dimension of the kernel of this linear map, which is V, right. Now, this dimension of the image, what can this be at most? Look, this we know that dimension of the image of V is equal to the rank of V, this is less than or equal to R, which is in turn less than n, sorry, not R, excuse me, that is going to be K, right, because we have chosen K to be the size here. So, now if we let this strict inequality hold, that is K is strictly less than n, because look, if K is equal to n, then you already have n linearly independent vectors, and that therefore is already a basis. So, that is of no interest to us. The only point of interest is when K does not have sufficient vectors to span the entire vector space C to the n, when it has less than n vectors, then we are claiming that we can still extend it to be not just any basis, but an orthonormal basis. So, starting with an orthonormal set of vectors which are less than n in number, we can always extract, we can always cook up new and new vectors, and until we get to an orthonormal basis for the entire C to the n, right. So, what does this mean? So, this means that n, now I am again referring to this particular step here. So, I am referring to this particular step here, this rank nullity theorem. So, n is equal to some r plus dimension of kernel of V, right. But now r is less than n, yeah, because remember this is r, right. So, the rank of V is what I am calling r, that is less than equal to k, less than or equal to k at most, but k is strictly less than n, right, and therefore, r is strictly less than n. So, therefore, I have the dimension of the kernel of V is equal to n minus r, which is strictly greater than 0. In other words, this dimension of this matrix that I have cooked up by stacking up these vectors V1 through Vk that belong to this set S as the rows, yeah, there of course, they are complex conjugates, yeah, the Hermitians, the transpose conjugates, right. This particular matrix V, unless k is equal to n, must have a non-trivial kernel. So, therefore, there exists some Vk plus 1 such that V times Vk plus 1 is equal to 0, because why? This Vk plus 1 must belong to this kernel of V. Now, of course, this Vk plus 1 is also equal to also non-zero, right. So, now what if I choose this Vk plus 1, what if I append S with Vk plus 1, that is cook up S bar is equal to V1, V2, up until this point you have all the entries of S, and then you just add this new fellow here. And the claim is that this is going to be another orthonormal set of vectors. Why? Because look, these fellows are anyways an orthonormal set, they anyway form an orthonormal set of vectors. Now, when you are adding one new vector to this set, all that you have to ensure is that this new vector is also orthogonal to each of these vectors, and I am saying that that is trivial. Why? Because of this. What does this mean? Now, look at the structure of V here. If you are writing here this step, this essentially means that you are saying V1 star, V2 star, dot 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 till Vk star times Vk plus 1 is equal to 0. That just means that Vi star times Vk plus 1 is equal to 0 for all I is equal to 1, 2 till k. So, therefore, Vk plus 1 is orthogonal to each and every one of those earlier vectors V1 through Vk, and therefore, this new set S bar that I have cooked up, which has a cardinality k plus 1, is another orthonormal set of vectors. Now, of course, you might say, what is the guarantee that it is orthonormal? Well, if this Vk plus 1 is not of unit norm, you just divide it, you better go ahead and divide this. So, if you found this Vk plus 1 hat, divide it by its norm, yeah, and then call this Vk plus 1. This is definitely going to be of unit norm, right? You can immediately check, take the inner product of this fellow with itself, Vk plus 1 with itself, and you will see that it is unit norm, right. So, therefore, given an orthonormal set, this is just one step. So, by induction you can now imagine that at the first stage you have picked up one vector. Now, you cook up a V matrix with k plus 1 rows and n columns in the same fashion as you did earlier, that is over here, and then you get any one of the arbitrary vectors that you have in the kernel of that newly constructed V. Normalize it, that is reduce its norm to unity through that scaling, suitable scaling, and then append it to the set. Keep appending the set till you have exactly n vectors. The moment you have n vectors, you actually end up with a bunch of orthonormal vectors, an orthonormal set of vectors, right. and which is also a basis for C to the n, right. So, that is one of the beautiful properties, that if you start with an orthonormal set of vectors, just like if you start with a linearly independent set of vectors, you can always extend it to a basis. If you start with an orthonormal set of vectors, not only are they linearly independent, but there is a straightforward way to extend it, at least when the vector space is Cn, yeah, there is a straightforward way of extending it to a orthonormal basis for Cn, okay. So, that is one of the interesting things that I really wanted to discuss, okay. So, having seen this, let me draw a line next to it. The next topic we are going to talk about is basically about, again we are going to go back to this, recall this particular vector space that we have dealt with earlier, yeah, the set of Hermitian matrices, all right, matrices whose, when you take the Hermitian operation, that is A is equal to A Hermitian, right, you take the transpose conjugate and they happen to be equal. So, all such matrices, they belong to this vector space, right. So, we have already seen that such matrices have a real eigenvalue, but now I am going to say that such matrices, that is Hermitian matrices, are always diagonalizable by a, or rather by an orthonormal matrix. Now, here I of course need to define what is an orthonormal matrix, right, because so far I have defined an orthonormal set. Well, it is, as you might have guessed by now, it is basically nothing but if you had ended up with this, where is that, this V matrix here with n rows and n columns. So, the final V matrix that you will get, right, will be an orthonormal matrix, or you can also sometimes call it a unitary matrix. So, these are interchangeably used in different textbooks, okay. So, a unitary matrix is basically if you have a matrix U such that U star U is equal to identity, okay, then you say that it is a unitary matrix, yeah, sometimes also said called an orthonormal matrix, yeah, alternate language, just, but essentially no difference. So, it says that you will always have this sort of a matrix U, which will take your matrix A belonging to this set vector space Hn, yeah, the set of Hermitian matrices or self adjoint operators expressed as Hermitian matrices in linear maps, such that they will be diagonalizable. Now, this is a big claim to make, and I will give you a sketchy sort of a proof for this. The proof involves mathematical induction again. Okay. So, you see that if you take the size 1, right, a complex number, it is always diagonalizable, right. I mean, you can normalize it, yeah, you get back the same number, it is trivial. So, true for n is equal to 1. So, as is usual, we will assume this to be true for n is equal to k, or let me choose some other number, maybe other symbol, true for n is equal to q minus 1, say, right. So, that means I am saying that it is true for h q minus 1. Now, we have to show that it is true for h q. Okay. So, any matrix of size q cross q, yeah, that will also be diagonalizable if every matrix of size q minus 1 cross q minus 1 and Hermitian is diagonalizable by unitary matrices, then so should every matrix of size q cross q, that is also Hermitian, right. So, let us try and proceed. So, what is our first step? Let A belong to this set HQ, and clearly because if it belongs to this set HQ, A has real eigenvalues. This we have proved in the previous lecture, right. So, A has real eigenvalues, okay, fantastic. So, if A has real eigenvalues, let lambda 1 be one such eigenvalue, right. So, if that is so, then we have A V is equal to lambda 1 V, right. We can always write this in this fashion, right. So, suppose we have this set V x1 x2 dot 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 till xq minus 1. Of course, you understand that V belongs to CQ, right, that is a given, and V is not equal to 0. These are just stemming from the definition of the eigenvector. Suppose you choose this matrix, this then belongs to C Q cross Q, and X is also unitary matrix. You can always do this. Why? By the preceding principle. Look, you started with one vector. So, one vector there is nothing to check its orthonormality, right. So, now given this one vector V, yeah, let us say this V is of unit norm, okay. So, let us say you have this one vector V, right. Once you have been given that this is one vector V, you can keep extending it by appending newer and newer vectors to it, yeah. And when you append newer and newer vectors to it, what you end up getting is an orthonormal set. Straightforward, right, just by the preceding principle. Once you have agreed that this is indeed true, this is what we have shown here, that any orthonormal set of vectors, when there is only one vector, all that you demand out of it is that it is at least normal. So, you normalize it, and then you add a second vector which is orthogonal to the first vector, and you have two vectors, and now the second vector also you normalize. So, you have two vectors that are orthogonal to each other and both have unit norm. So, you have a set of two vectors that forms an orthonormal pair. Now, you construct this matrix of size 2 cross Q, right, and find out any vector in its kernel, yeah, that is going to be the third vector, right, normalize that, append it to this set, you have 3 vectors now. So, you keep going like this, and these are your x's, right, at each step you keep adding one such vector. So, first stage you added this came in, the second stage, second iteration this came in, at the q minus 1th iteration this came in until it formed a basis, and once it forms a basis, then this is bound to be true, an orthonormal basis, then this is bound to be true that X will be a unitary matrix, all right. So, this at least we understand, right. Now, look at this A X, what does it look like? You have A V, A x1, so on till A x q minus 1. And what if I hit it on the left with this x star? So, this is going to be, so I am continuing from this step here, although I pushed it to the left here, this is going to be nothing but V conjugate x1 conjugate till x q minus 1 transpose conjugate, right. And this is A V. Now, what is this A V? After all, V is an eigenvector of this, right. So, this is nothing but, I can write this as lambda times V, yeah, but as for the others I do not have that benefit, right. I have to write them as A x1, A x2 dot 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 till A x q minus 1 likewise. Now, if I were to open it up and write the entire thing, it might look a little nasty, but do bear with me. So, I am going to write this down in a very simplified fashion. This is going to be lambda V star V, this is going to be V star A x1, V star A x2 dot 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 till V star A x q minus 1. Apparently nothing special about it, but what happens from this step onwards? When this gets multiplied with this, well, this lambda is just a scalar. So, x1 star V is 0, because you know x is an orthonormal or rather a unitary matrix, right. So, this is all zeros, all of these will be zeros, and as for this part I really do not care, yeah, as for this part I really do not care what happens here. But remember that this has a size q minus 1 times q minus 1, and more importantly you notice that if I look at this x transpose A x and if I take its conjugate transpose, what do I get? I get x transpose A transpose x, but then A belongs to H q, and therefore, this can be written as x transpose A x, right. So, therefore, I can conclude that x conjugate transpose A x also belongs to H q. In other words, this is also a Hermitian matrix. If this is a Hermitian matrix, then of course, there are other ways of reducing this, I am taking the shortcut. So, if this is a Hermitian matrix, then well, this entry here, this 2 1 entry here must be equal to this entry here. If this is 0, then this must also be 0, this must also be 0. There are other ways of seeing this also. You can just take this V conjugate transpose V Hermitian A and then replace this A with A Hermitian. So, then you will get this as lambda star V Hermitian by the eigen equation, and V Hermitian x1 is 0. So, there are multiple ways of seeing why this should also vanish. So, then this, let me just keep this as an aside here. This then means that I have the resultant being lambda, a row of zeros remaining here, a row column of zeros below it, and something sitting over here. But what do I know about this something? Look, I have already told you that this belongs to this set. So, therefore, this part must also be symmetric and belong to H q minus 1, because this has a size q minus 1 cross q minus 1, because if this were not also Hermitian itself, then this overall matrix cannot be Hermitian, no. So, this small part, let me put that on with a different ink here to make it clearer. So, this smaller part that I marked out here, this q minus 1 cross q minus 1 block, this had better belong to H q minus 1, right. If it does not belong to the H q minus 1, then this overall matrix of size q cross q will also not belong to H q, but that is a clear contradiction, because I have shown you that this belongs to H q, right. So, therefore, what we can now deduce is that, well, by hitting with this x star A x, we get to this form. But now, by the principle of mathematical induction, whatever this star is, so this starred thing, let me give, okay, since I have not given it a name, maybe it is too late in the day. The starred thing which belongs to H q minus 1 can be written as some, say, x hat, just like this one can be written in this fashion, can be written as some x hat and some diagonal times x hat. So, x hat conjugate. Why? Due to mathematical induction, nothing else. We have already assumed that any matrix of size q minus 1 that belongs to H q minus 1, which is implying that it is a Hermitian matrix, right, must be diagonalizable, and then we are attempting to prove that it must be true for the size q as well. So, this is true due to mathematical induction, this is the inductive step, the assumption that we have made. So, therefore, there must exist some such x hat such that this x hat of course belongs to size C q minus 1 cross q minus 1, right. This must, and this must also be a unitary matrix, yeah. So x hat star times x hat is also equal to identity of size q minus 1. This is due to the mathematical induction, the inductive step, right. So now can we not then see that, suppose I were to replace this here, I have x star a x is equal to lambda zeros here, and this one I am going to write as this x hat star, this lambda, this is lambda is also a diagonal matrix, yeah, or containing the eigenvalues of the smaller sub matrix. So, this lambda is also q minus 1 cross q minus 1, my bad. Right? Yeah, there we are. But now this I can also write as, notice very carefully, as 1 with zeros here, x hat star. Convince yourself that this is indeed so. So, notice that this is a single scalar and this is also a diagonal matrix 1 0 0 x hat. Okay. We are convinced that this is true because you can just multiply. If you have any doubts about the fact that this is indeed expressible in this form, just go ahead and multiply and you will see that it immediately follows straight away, right. That is the easiest way to check anything for that matter, yeah. But now once we have written it in this form, we do not stop there, but now we want to write this a, right. So, we have a is equal to, let us hit this on the left with x, both sides we hit by x. So, because x is a unitary matrix, x star is equal to identity and x star x is also identity. So, we hit this with an x and we have this 1, the zeros, this x hat star, and then we have this diagonal matrix. So, this is our overall diagonal matrix, and on the right we have 1 0 0 x hat times x star. Okay. So, therefore, we have that this matrix A, which belongs to H Q, can always be diagonalized. The only thing that remains to be shown is that this overall matrix, that is, let us say this matrix and this matrix are indeed like orthonormal to each other, yeah. So, this is indeed that any one of them is either of one of them is at least a unitary matrix. How do we prove that? Well, for starters you can immediately see that you take the conjugate of transpose conjugate of any one of those fellows and it results in the other fellow, right. That is easy to see. So, for example, you take x and times 1 times 0 times x hat star, take this whole, let me not use that bracket, yeah, right, take this whole fellow's transpose conjugate, Hermitian, okay. Then of course, the order of multiplication gets reversed. So, this becomes 0, the 0 part remains the same and this becomes x hat, right. So, one is a conjugate of the other, but now we have to also show that these are unitary. So, let us try and multiply them. So, we have x 1 0 0 x hat star times 1 0 0 x hat times x star. So, first we do the multiplication between these fellows that are inside. So, this leads to x. So, again we multiply, we see that this is 1 0, right, and this also leads to identity of size q minus 1. But what is this? This is after all nothing but then reduces to identity of size q. So, then this leads to x star, which is nothing but identity. Therefore, these matrices that appear as paddings on the left and right of this diagonal matrix here, they are not just conjugates of one another, complex transpose conjugates or Hermitians of one another, but they are also, their multiplication leads to the identity. So, this matrix is also unitary. So, therefore, this claim that we made that any matrix that is Hermitian is unitarily transformable to a diagonal matrix holds true, right. This is a very, very important conclusion, and this will pave the way towards one of the most significant factorizations that you are ever likely to come across in matrix theory course, that is the singular value decomposition. This forms the bedrock on which you base that singular value decomposition, which we will claim in a while. Okay. So, now having seen this far, we are now in a good position to look at some other definition. We can call it, we can draw a line below this and say that okay, this part is more or less kind of done. We have studied the properties of the eigenvalues and eigenvectors of these Hermitian matrices, right, belonging to Hn. Yeah, we have found out all there is to know about their eigenvalues and eigenvectors, that is the spectrum, right. So, now we talk about something else which eventually will also be related to their eigenvalues. Because these eigenvalues are real, it actually makes sense to talk about their signs. You see, if you have a complex number, you cannot say whether it is positive or negative. You can talk about its real part, whether the real part has positive sign or negative sign, but you cannot really talk about the eigenvalue being positive or negative. But on the other hand, if you have now a Hermitian matrix, because we have already proved in the previous lecture that its eigenvalues must be real, it therefore makes sense to talk about the sign of these eigenvalues. And it turns out that what we will next define is so called positive definite matrices or positive semi-definite matrices. With a little bit of tweaking, just flipping the inequality sign, we will also get what we call negative definite and negative semi-definite matrices. So, everything that I will talk about when concerned with positive definite matrices or positive semi-definite matrices, I urge you to also read them as negative definite and negative semi-definite matrices with the inequality signs reversed. Okay, those results will be still true. Okay. So, here is what the definition of sign definiteness, or rather positive definiteness, sign definiteness of matrices in Hn. So, we will restrict ourselves to Hn simply because for general matrices there is no guarantee about what the signs will be. Okay. So, therefore, we will restrict ourselves to only matrices that are Hermitian. Okay. So, how do we define this positive definiteness? Suppose for a matrix Q that belongs to this Hn, we have x Hermitian Q times x, yeah, greater than 0 for all non-zero x belonging to Cn. All right. Suppose this is true, then Q is said to be positive definite. Recall that Q times x is still a vector, but when you hit it from the left with x star, that is the x Hermitian, then it becomes a scalar, right. And this scalar we are claiming is always going to be positive if and only if, this is the definition. So, if the scalar is going to be positive, then we call such matrices as positive definite. By the same token, now if you introduce this less than strict inequality. Yeah. So, then you will introduce the so called semi definiteness. Okay. So, I have written both in red, either you read only the blue part and then you will have the definition of positive definiteness, or you read both the blue and red parts and then you will have the definition of semi definiteness. Okay. So, that is how we define it. Of course, for negative definiteness just flip the sign. So, this is basically how a positive definite matrix is defined. But that is all well and good, you might say. I wonder, how do we check, given a matrix, do we have a quick and ready test based on what we already know? Do we have a quick and ready check to figure out if the given matrix is positive definite, negative definite or indefinite, right? So, it could be that for a given Hermitian matrix and some vector, this really leads to a positive sign, the scalar is positive. For some other vectors it is negative, and for some other vectors it is 0. In that case it is an indefinite matrix. If it is always negative for non-zero vectors, then it is negative definite. If it is negative or 0 for all vectors, then it is negative semi-definite. Yeah, same thing for positive definite and positive semi-definite. So, you can have all 3 possibilities, or rather all 5 possibilities: positive semi-definite, positive definite, negative semi-definite, negative definite or indefinite. Yeah. So, all of these 5 possibilities are wide open, but then how do you check for it? In other words, how do you figure out which one is it? Given a matrix, a definition can only take you so far, but we need a test, need a way to figure out, right. So, then it turns out that this, what I am now going to claim, is going to give us a handle over this. So, Q is positive definite. So, I have left that space, you can easily guess, because I am lazy and I want to include this possibility of semi definiteness in the same space. This implies that all eigenvalues of Q are greater than or equal to 0. So, this goes both ways, it is an if and only if condition, it is a necessary and sufficient condition, alright. So, let us quickly try to figure out, at least if not prove it completely, at least try to figure out why this must be so, right. Okay. So, here goes. Suppose you have this Q belonging to Hn. By the preceding result, Q can be written as some x Hermitian times some diagonal matrix, which is of course real and diagonal, because the eigenvalues are all going to be real, right. This is how you can write it. Now, suppose some eigenvalue of Q is negative. Okay. So, we are going to then rule out the possibility of this matrix being positive definite or positive semi definite. Okay. So, without loss of generality, let this be lambda 1. So, what is this lambda 1? So, this is basically, if I order it, give it some order, then this is lambda 1, lambda 2, like this till lambda n. So, suppose lambda 1 is negative, already we know it is going to be real. So, in addition to that, we are imposing the condition that it is negative. Now, suppose x belonging to Cn is such that x times x, yeah, what is this x? This x, remember, x times x is equal to 1 0 0 0 0. Remember, this I have done without loss of generality. If, for instance, instead of lambda 1 I had chosen lambda 5 to be negative, I would have taken this, in this equation I would have taken the fifth entry to be non-zero and unity and all other entries to be 0. So, this is without loss of generality. So, let us say without loss of generality, there is this and lambda 1 is negative. Okay. So far so good. Now, the point is, can we always find such an x? Well, of course we can, because then x turns out to be just x, this big X Hermitian times 1 0 0 0 0. Why? Because of course this x is unitary, therefore its full rank, because you hit it with x star on the left or right and you get identity. So therefore this is clearly such a choice of x. Yeah. But now what happens with such an x? Therefore x Hermitian qx is going to be equal to x Hermitian, or rather let me open it up like this. With this choice of x, x Hermitian is going to be, hang on, yeah. So this is 1 0 0 0, yeah. So remember, if this is x, then x Hermitian is going to be 1 0 0 0 till and then x. The order gets reversed, right. This is x, and we have that q is equal to x Hermitian lambda x. So this is x Hermitian lambda x, okay. And finally we have lambda x, sorry, my bad, lambda x, and finally we have x starred 1 0 0 0 0 like this, okay. So if I were to now mark it out for ease of reference, this x is this, let me use a different color, purple, yeah. This q is this, okay, and this x is this, right. So there is no problem about in going about in this fashion, right. Now what happens? Look, these two can be combined to give identity, these two can also be combined to give identity. So what I then essentially end up with is 1 0 0 0 like this, and then this lambda 1 lambda 2 dot 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 till lambda n, and then this 1 0 0 0 like this. But what is this going to pick out? This is going to just pick out lambda 1, which is negative. So therefore if any of your eigenvalues happens to be negative, I can always find an x such that x Hermitian qx is going to be negative and it cannot be positive definite. So therefore having all your eigenvalues positive is a necessary condition for a matrix to be positive definite. But I wonder if it is sufficient, okay. So for that, so this necessity is proved. So necessity is proved, but I wonder if this is also sufficient. Is it? Let us check. Let x belonging to Cn be any arbitrary vector, right. If it is any arbitrary vector, then I can easily express it as a linear combination of some fellows in a basis, in a given basis, right. So it just depends then on what sort of a basis I choose. Here I already have a ready-made basis, no. Look, the columns of x is a set of orthonormal, or rather, yeah, orthonormal vectors, right. So they form an orthonormal basis, yeah. So suppose x has columns given by x1, x2 dot 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 till xn. When I say suppose, I mean that I am just writing out the columns of x as individual vectors. Now x1, x2 dot 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 till xn is an orthonormal basis, quite simply because x is a unitary matrix by my definition. So, this is an orthonormal basis for Cn, no doubts about this, right. Therefore, I can write that x is equal to summation Ci xi, right. So, I can write this as a linear combination of the fellows in the basis, no problems whatsoever with that, is it not. Now, if I am saying that this is to be a sufficient condition as well, then it should turn out that I must assume that all the diagonal entries are positive, all the eigenvalues are positive, right. So, say okay, let me rewrite that a little. Say A belonging to Hn, or rather Q have I chosen, right, I have chosen Q, so let it be Q. So, Q belong to Hn has all its eigenvalues positive, alright. So, suppose this has all its eigenvalues positive, then what can I say, that Q can be written as x Hermitian delta x, where delta is a diagonal matrix with all its diagonals positive, right. Okay, excellent. But now, how can I write this x then? X, you notice, can be written as x1 c1 plus c2 x2 plus dot 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 till cn xn, which is nothing but x1 x2 dot 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 till xn times c1 c2 till cn, and this is an arbitrary vector that I have chosen, right. Therefore, x star qx is going to be nothing but, you see, what is this x star? Let me just make a footnote of this. So, this is going to be nothing but C1 conjugate dot 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 till Cn conjugate, written in the row form. The order of multiplication gets reversed, as I have already explained. Yeah. So, this is basically nothing but the x. So, then this becomes x star. This was x times the vector c, now it becomes c star, the row vector times x star. So, this is going to be what? C1 star, yeah, okay. It really matters not, but just, you know, to be clean on these calculations, this is not really a big deal, as you might see. So, what I am saying is that these x1s that I have chosen, right. So, let us say I take x1 star, okay. So, the columns of x1 star are also going to be an orthonormal basis, okay. The simple reason is that, well, you have x star x is equal to x star is equal to I, yeah. So, whether you choose the columns of x or the columns of x star to be your basis, it matters not, right. So, let me choose it, because that will make the calculation simpler, okay. So, this is x star, okay. So, therefore, this is going to be x. So, now I get this C1 star, C2 star dot 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 till Cn star, yeah, and then x, and then this is basically this part, and then I write down q as x star lambda x, which is this q here, and finally this x I can write down as x star C1 C2 dot till Cn, right, which then leads to again similar decomposition. I mean, these two are pulverized, so this becomes identity, this also becomes identity. So, I have basically then C1 star dot till Cn star, in between I just have this lambda, and finally I have here C1 dot till Cn. If I now carefully write this down, this lambda I can open it up as lambda 1 till lambda n, then this is nothing but lambda 1 times C1 modulus squared plus lambda 2 times C2 modulus squared plus dot till lambda n times Cn modulus squared. Now, so long as this vector x that I have chosen is non-zero, that is to say that at least one of these CI's is not 0 and all your lambdas are positive as per our assumption, this is clearly going to be greater than 0. So, therefore, this is also a sufficient condition. So, in other words, we have proved that if all your eigenvalues of a Hermitian matrix are positive, they are going to be real by default anyway, we have seen that earlier. But if all of them are positive, then that is a necessary and sufficient condition to claim that the matrix is also positive definite. You can just plug in similar conclusions about semi-definiteness as well. In the next lecture, we shall get into singular value decomposition, where we will make use of these properties of Hermitian matrices and unitary matrices that we have described here. And finally, once we are done with SVD, we will hopefully be able to get back on track into more of control theory. So, until then, take care. Thank you.